Hello, hello, hello. Can you guys hear me? Can you type something in the chat? Okay, let me see about that. Also, if you're not logged in with your Google account or whatever, you probably want to be, since we will be using the chat to interact. I don't know if you can chat without being logged in. And yeah, you kind of need to interact in the stream. It's not a lecture that you just watch. Yeah, it doesn't have to be your UMBC account. You can use your normal account if you want to. That's fine. Oh yeah, Krita is gonna be our blackboard. Well, whiteboard, whatever. It's gonna be our board. So I've maxed out all of my microphone levels. I'm not sure if this is any better. Okay, good. So, yeah, let's get started. So, well, the title is technically a C refresher, but we're gonna go over a lot more stuff. Also, yeah, if you have other things to do and you need to leave, just leave. This is not a lecture. There are no participation or presence or whatever required. So, first of all, we're gonna go over some theory OS stuff. Some of that you should have covered on 313, I believe. Also, what's 313? I'm not quite sure. What's the title of that course? Anyway. Some of that you should have covered on 313 and assembly. Okay. And some of that is gonna be covered on 411, I think, which is the architecture. And some of you might not have taken architecture yet. So we will go over some stuff. While I'm talking, you might have a question, but by the time you finish typing up the question, I might have moved on. Just finish typing up that question and send it. That's okay. That's normal. That's what happens with online learning and everything. I don't think that 411 is a prerequisite for this, but knowing that stuff helps a lot, actually. And you should know that stuff before going to OS, but that's not my decision to make anyway. That's why we're gonna work towards a working understanding, and we're not gonna go into deep detail, but still it's gonna Yeah, it's gonna be there. The first thing that we're gonna talk about is compilation. All right. I think that you're used to Python a lot, right? And there, when you're using Python, you have the executable, which is Python itself, and then it's reading your .py script. And what it does is, while the executable is running, it's gonna read line by line and convert it into some form of machine language at runtime that depends on your system that you're currently running, and then execute. While what we're doing here with the kernel and your project one and C and everything is you have your source code, you convert it offline into machine code, and then that runs directly on your hardware. Right? That's the compilation step. That's taking your text, your source code, and converting it into a binary, an executable. Right? So let me do. This is my VM. Linux. Okay. I have a different version of Linux here. It's okay. Doesn't matter. Let's give it a second to load. Alright, so all of these things in here, all of the C files and other files and our files are part of the source code. Okay, this is what you cloned originally for Project Zero, for example. Right? And during the build process is everything. It includes compilation, maybe some pre-processing if it's required, creating the packages, all of that stuff. Right? And during the build process, you created a deb file, right? That was the Linux image, whatever, blah, blah. Right? This is a binary file. And it's the same as when you compile a simple program where you get the a.out, for example, or an executable an out.exe in Windows. This is equivalent. A deb file is just a file that Debian and other similar distributions know how to install. Right? And then you get the thing, you install it as a new version, as a different version of your kernel, and then you can run it. And this is where some confusion comes in. So let me bring up a VirtualBox again. Here. Okay, so this is the grab menu we've talked about a little bit on Piazza. Now, when a computer starts, the first thing it will do is go through the BIOS, which we missed because I was not quick enough. And then after you're done with the BIOS boot up process, you get your, what's it called? Your bootloader. The bootloader is a piece of software that has some, specific API, and it knows how to start on an operating system. Multiples, usually. Right? So right now we are stuck in the grab screen. When I hit enter here and it starts loading, what it actually does is it finds the kernel executable, the deb file you installed, and starts it. That's all the kernel is, basically. It's just a program, an executable, that starts before everyone else. That's it. And then when that executable starts, it's going to create your environment, your desktop, and your processes and all of that stuff. Right? So the kernel is the first executable that starts. And that's why you had to reboot to get your changes after you installed it. Right? So since the kernel was already running and you installed a new one, you had to restart the program, basically. Right? But since the kernel is the lowest program, is the number one program that runs, you have to restart your computer. Everyone clear with that so far? Anything that you would like me to go over again? This is just some context about what you were doing so far with Project Zero and all that stuff, and you will be doing a lot actually through this course. Good. The kernel linked at boot depends on what you mean linked, like as in linking during the compilation process linking, or just connected? So the kernel itself as a binary, when it is compiled, it is linked and linked to itself, if that makes sense. And then when you run whatever other program, the way compilation for that other program works, so the compilation process for a kernel is a little bit different for a normal program that you write. And the way that compilation works is it leaves some space, and we will talk about that soon, so that the kernel is linked at runtime to that process. And it's not completely accurate to say linked, it's more like mapped. Yeah. So, on to some more theory stuff. So you've all heard across your classes that the stack grows up and the stack grows down and the heap grows up and all of that kind of mumbo jumbo. All right. Now, when back in the DOS days, you could access the whole memory, the whole system basically. Every process could access everything, including every other process, which created a lot of issues. Right? And then we had to somehow fix it. And that's where virtual memory comes in, and it's going to be a huge part of your material later on in the course. We're not going to really bother with that now, but it turns out that programming model that DOS was using, where everyone can do everything and can access everything, was really easy to code for because you didn't have to care about anyone else. And you could do whatever you wanted, and as long as you were okay, everything was okay. Right? So we simulate that, and it still holds. So most programs still work with that mental model. It's not the actual model, but they work with that mental model. So every program thinks it has control of the whole memory. So let's say that we have 100 bytes over here, right? This is our memory. It's smaller numbers, so we can work with them. Right? And yeah, every program thinks that they have control of the whole memory here. What really happens is the executable is just loaded into memory. So the thing you have on your hard drive. And the first part here is some, let's say, intro stuff that tells the program how to start, and Windows or Linux how to start it. Then you have the actual kernel that is mapped in here. Right? And then you have the static component, static part, and all of that, and the text segment you have probably talked about in 313. Right? And then that's what gets put into your RAM, basically. And then let's say that part finishes somewhere around here, all of that, kernel, static, whatever. the rest of the memory space is your, say, running space. So some part of this is going to be your stack, some part of this is going to be your heap. So let's say that my stack is here. I want to say that this is address 80. And I want to add something to it. Right? I'm pushing a new variable. What address am I going to push that variable to? Is it going to be over here? You can see that. Is it going to be towards the 99 address or towards the 0 address? Guys, I'm going to need you to participate a little bit. No, towards the 0 address. That's what the stack grows down means. That the stack grows towards lower addresses. Okay, so when I add something to my stack, it goes here, and the next thing goes here, and the next thing goes here, and the opposite goes for the heap. When you add something, you go towards higher addresses. Now, those do not really have to be that way, so it doesn't really. It's not mandatory to have the stack on the right and the heap on the left, and they grow towards each other. But that's a simple mental model to work with, and it's fine. It doesn't make a difference. So let me remove all of that. See the next thing. Okay. Yeah, this is also. Now, when programming, we have what's called a stack frame. Every function you call, or scope you create sometimes, what we don't care about, every function you call creates a stack frame. And that's where all the memory for that specific function resides. So where's here? Right, so we have our main function. It creates a stack frame. Let's say that stack frame is here. Okay. I'm not really sure I know why it was implemented to grow downwards, but I'm guessing it's maybe at some point it made operations easier. And I'm not sure it still does, or if that's any relevant anymore. But it is what it is. So some of that has to do with backwards compatibility issues, and we still might be using this because, I don't know, at some point it made sense, but not anymore. We have our main function. Let's say that this is the stack frame. This whole box here is the stack frame for the main function. When I call the stack populating function, it's gonna create another stack frame down here. Now, those stack frames do not necessarily have to be the same size. Okay? It really depends on what exactly you're doing in that function. Right? So, whenever you call a function, you create a new stack frame and you move your code, your execution, let's say, moves on into that stack frame. And the layout of a stack frame is you have some space for your locals. Locals being the function or the variables that you declare in that function. And that part is inside the stack frame itself. So after the base of the stack frame, and then your arguments, potentially. right? No, it's okay. That's why you're here. You're here to ask a question. A stack frame. A stack frame is, let's say, the object that you put inside the stack. It's not a concrete thing, as we'll see. But let's say you were writing C++ and you had a vector of integer, right? Well, this would be a stack of stack frames. You need a common thing to add to your data structure so you can keep using that data structure with whatever happens, like with arbitrary code and memory. So you have your locals. The local variables are inside the stack frame, let's say. So they are towards the lower addresses, but the arguments are above the beginning of your frame. Technically, it's like they belong to the previous frame, if that helps to think of it that way. But you do not always have that space for the arguments because you do not always need it. Nope. Nope. Okay, and let me see what else do I have here. Yeah, so all the addresses for the locals are the base pointer minus something, since it's going down. It's going downwards. And all the addresses for the arguments are the base pointer plus something, since it's a higher level address. So if this stack frame was over here, the arguments are up here, and the locals are in here. This is how a computer works. It doesn't have to do anything with whatever language you're using and everything. Right? So Python just hides this stuff from you, for example. It's not that those things do not happen in Python, it just hides it for you. C, on the other hand, doesn't. Well, at least it doesn't hide it so much. So, let's go into our code a little bit here. So again, you have your main function and the stack populating function, and that would create a stack frame. So let me see if I can put those side by side. Yep. Right, so calling this function would create this stack frame over here. Actually, I don't think you can see it. Right, calling this function would create something like this. And let me delete those. Oh no. And these are the locals. So A, B, C, and D would be in here. And arguments which we do not have would be either up here or in registers. During the very first lectures, you should have covered some piece that said that you have 3 ways of passing arguments to a function: through a pointer, through a shared memory, through registers or something like that. Well, technically you pass stuff through through the stack, through pointers and through registers. Technically you pass stuff through the stack and the registers. The pointer thing is not used so much on its own. Let's see, let me close this. Is everything clear so far? Anything you would like me to cover again? Yeah. Okay. Now, RBP or EBP, if you're doing 32-bit assembly, is the beginning of that specific stack frame, usually. Now, this is completely off topic, but modern compilers have gone away with a lot of that stuff. So there are cases where you have new functions and you do not create a new stack frame because you don't need to, and that's for the sake of speed, and that's completely out of scope to what we're talking about. We don't really need to care about. A little bit about the environment where we will be seeing our code and playing with that stuff. If you see this no inline thing, pretend it doesn't exist. It's just there so we can see some stuff during compilation and decompilation and all of that. You don't really need to care about. No. If I hit execute, if I start running, what you can see right here is this yellow arrow down here. It means that execution has stopped at this line. So right before we execute stack populating function, this is a breakpoint. Right? Down here on the watch window, we will be able to watch different variables for their value and how they change. And where's my memory? My memory is not here. Hold. I'm sorry. Memory 1. And this window over here right now is this. My whole computer memory, in quotes, as the program sees it. This is the actual raw bytes that are stored in RAM. If I step into the stack populating function, now I'm in this function, and I'm gonna go to disassembly to see some assembly. You have your typical push EBP, move EBP, ESP. This is how you start a stack frame, basically, in 32-bit assembly. x86 32-bit assembly. But yeah, we don't really care about it. Next thing that happens though is to subtract 18 hex. I'm going to bring up my calculator here. If I type 18 in hexadecimal, you can see that it's 24 in decimal. This is the space for your locals. Okay? So this is the space for those 4 variables. Actually, for now, let me make this an integer. Right? And it's going to be the same number again. So if I go again to this assembly, see, it's still, so it moves the stack pointer 24 bytes down. This is the space for the locals. As you can see, A, B, C, and D do not exist. Right? They're just places in the stack. A is not a thing. It's just some memory that we refer to as A. Now, because we are used to that and it makes sense, Visual Studio and the Microsoft version of the assembly and all of that stuff, it still keeps A here as a reference. But in reality, it's EBP, the base stack pointer, minus 4. Right? And B is EBP minus 8. But this is that way. It is shown that way here, so we can, reason about it and debug it easier. So this is what I want you to take away from this part, that your locals are basically just space in the stack, in the specific stack frame. And there is nothing that makes A. It's just there. So, I'm not sure we really need to go, but okay, yeah, we can go over this stuff here. So this is before we call my function do. Let's go to disassembly. This is where we call my function do. And the instructions, the first thing that it does, it subtracts 20, so it makes space for 20 hex bytes on the stack, and it starts moving things around. Anyone care to guess what those 20 hex bytes are? Like, why do we need to create that space? So, the reason we need to create register states are either saved explicitly or in the process block. Okay, repeat the question. The first thing we do before calling my function do is to create space for 20 hex bytes, which is for 32 bytes. And then we call the function. We move some stuff around and then we call the function. No. What happens here is we have this s as an argument to my function. And as we said, the arguments right before that stack frame. Right? So this is creating space for arguments, for my struct s, basically. So your registers are 32-bit, 64-bit, 8, 16, 32, 64, 128 bits. You cannot store any data larger than that on a register. Significant in what sense? So that's the registers are of that size to accommodate how much, let's say, data a CPU can push per cycle, basically a word, the size of a word. So registers used to be the exact size of a word. Now they are usually double that because you can process multiple data at the same time. That's irrelevant. Basically, a 64-bit CPU can address 64 bits at a time, and a 32-bit CPU can address 32 bits at a time. And also 2 to the 32 is 4 billion something, and that's why older operating systems like Windows XP would only see 4 gigabytes of RAM. But since you map the kernel onto the first part of the program, and the kernel was usually about 1 gigabyte, that's why you could only see 3 gigs of RAM, because the rest was just the kernel memory. The more you know. So, anyway, back to the disassembly. So the first thing it does, it creates some space and moves S whatever s is into it, and then it calls my function. So if I go into my function and go see the disassembly again, okay, it starts doing things and moving stuff around. So where is it? See, again, here the assembly is written in a way that it's easier for us to understand. So s subscript whatever, it's the same as saying wherever s is, which is up here, plus something. So again, it's relatively to the base stack pointer. Okay, so while it's written as s here for us to visualize better, you're still accessing RBP plus something, which is where's my code? Which is where we moved s. So this s over here and RBP plus something, they're not the same. S belongs to the main stack frame. RBP plus something belongs to my function 2 stack frame. It's just a copy. This is going to be really, really important to remember and understand. That's why I'm spending so much time on the prologue right now, because it's going to make everything else make sense. The moment this thing that, locals are here, arguments are here, and they are different from whatever was in the previous function, the moment this differentiation makes sense, that's when C is going to make sense to you, basically. So do you want me to go over anything here again? Okay, I'm guessing not. Cool. Next thing, strings. So this is a macro I've made, we don't really care about. It's gonna tell us if string 1 is equal to string 2, string 1 is equal to string 3, and string 2 is equal to string 3. So try to guess what will happen. This is string 1, this is string 2, and this is string 3. Are those equal? So let's learn and see. Let's see the first one. Let me bring the output here. String 1 equal to string 2. False. String 1, string 2. Those two, they are not equal. String 1 to string 3. Whoop. Also not equal. String 2 to string 3. Also not equal. So a string is basically just an array of characters. String 1 and string 2, they're different pieces of memory. So since they are different pieces of memory, the pointers are different, so they're not equal. Even though the text is the same, it doesn't matter that the text is the same. We don't know that it is text. A car is not text. necessarily. A char is just a signed byte. That's it. It's not text. You don't. That expression is never true, with one exception. Let me go to the properties here. And this is a point of confusion. Let's go to optimization. As you can see, I have optimizations completely disabled. If I do enable them, favor size, I don't know, both should probably do the same. If I enable them, Ezra, while that would give you true, it will not give you true for the reason that you think it does. And I will get to that soon. So now that I enabled optimizations, as you can see, string 1 and string 2 are equal. And you will commonly see this. So while the compiler was compiling my code, it noticed that the text of these two things were the same. So it just created one copy of the text and made both string 1 and string 2 point to that one copy of the text. And this is why they are equal, because they're pointing to the same memory. It has absolutely nothing to do with the text that they contain. Static is basically, it means global. In reality, what it means is, as we said up here at the beginning, you have multiple segments. One of them is the text segment, one of them is the data segment, right? And one of them is the static data segment. Everything you name static ends up in one of those segments. Right? So I'll get to it in a bit. So everything you name static ends up in one of those segments, and it has a fixed address, and that means that everything in your program can see it. That's how it becomes global. Now, the reason your code, Ezra, would return true is if you dereference string 1 and string 2, you get 8s. You don't get hello world, you get 8s. And both have 8s in the same place here. So 8 is equal to 8. 8 is a character, is a value that C knows how to compare. Right? So 8 is equal to 8, you would get true. But you would also get true if the first string was this one. That's H, not 8, unless I'm misunderstanding. The letter H. Yeah, you know, my accent is a little bit heavy. What can I do? I'm trying to fix it. So, if your code, Ezra, would still give true here. The only way to, yes, if you dereference a string, so we will talk about pointers again. Exactly. We will talk about pointers again, but basically when you dereference a pointer, this is a car pointer. So if I dereference it, I'm looking at a car. I'm no longer looking at a string, let's say. The correct way to do it is go character by character and compare character 1 with character 1 on the other string, right? That's the only way to do it. That's what every other language does, that you can use equals equals to compare strings. No, C does C++ does the exact same thing. C++ has the exact same behavior. But you can compare std strings, which is a class now, and it overloads the equals operator. And when you use equals, it will go character by character and compare the two strings. Right, so you still, that's the only way to compare strings, character by character. There is no other way, no matter the language. It's just that some languages give you an easier way to do it, or more intuitive way. And let's print the strings. As you can see, all three strings now print hello world. This thing and this thing, they are the exact same. Actually, the compiler converts this thing to this thing. Oh, I just enabled optimizations, and the compiler figured out that these two pieces of text are the same and made one copy of it and had both strings point there. Right, so in GCC, if you have O3, the O3 flag for the optimizations, it's going to do that. That's why you often see that misunderstanding there. Now, if I remove this 0 at the end here, who wants to guess what's going to happen? We've got a bit of extra printing down here. I'm surprised it didn't just crash. So C strings need to be terminated by a 0, by a null. What happened here is I had a few more bytes. It looks like I had at least 3 bytes, I don't know how many, and somehow it found 0. Right, so it started reading. At some point, it found a 0 and was like, yeah, this is the end of the string. You are gonna do this a lot for Project Wine. You're gonna make this mistake a lot. So if you start saying garbage characters printed or random segfuls when you're printing, it means you do not have a 0 here. Yeah. So this was the prologue. It was lengthy, but if you get this, especially the stack thing, you are more or less done with C. The rest is, just looking stuff up online and minor intricacies. That's it. So let's get into the actual content now. Our first section is called Everything is Bytes. So as we said, everything is on the stack or on the heap, as you probably know, and it's just bytes. So here I have 2 structs, one called potato, the other called message. They both begin with an integer, but the message has a float after that. Do we need this part? Okay, ignore this section for now. No. In C, this is how you create a struct. This is almost like a class, but not really, because it is just data. You do not have any behavior. You do not have any functions. It's just data. And whenever you want to reference this data type, which is called struct message, you have to type struct message. As you can imagine, it gets boring having to type all of that. So you can type def one thing into another. So you're saying to your compiler, yeah, I know there is a thing called struct potato or struct message, but I also want to call it potato t because it's shorter, or for whatever other reason. Right? And now your compiler knows that these 2 types are equivalent. You could also do it this way. in one line. The underscore T part is a Unix convention. It means type def, and it's usually there to show that, this is not a real thing, it's a type def to something else. So you might want to check what that else is. And in Windows, for example, the way they do it is, if I want to call the struct called potato is tag. Okay. But yeah, we don't really care about that. That was just a useless piece of information for the day. Right. Let's see here. So, as I said, are you guys familiar with unsigned? What this means? So, if you've done, I think it's you do that in 4.11 about one's complement and all of that. So, if you have a byte in binary, it's 8 bits. No, that's not. Oh, unsigned binary, yeah. Yeah, well, that's the thing. A car, you need to stop thinking of car as characters, although that's where it comes from. Car means a byte in size. It means 8 bits. So if you have a byte, which is 8 bits here, if it is unsigned, you're using all 8 bits to represent the number. If it is signed, or it has nothing in front of it, it means that the first bit represents if it's positive or negative. You do other things. If you've done two's complement, if you covered that, you do other things. We don't really care about those other things right now. We just care about the first sign. Let's say the purest representation of data is an unsigned car or unsigned char, whatever you want to call it. Right? This is the definition of a byte. If you in C++, if you type byte, it's basically an unsigned car. Right? And you can see that this gets confusing pretty fast. So we have the standard integer representation. If you include this header in Windows, Linux, whatever else, in the kernel, they have a different version of the exact same thing. You get the standard representation of an integer. The way it works, you have U for unsigned, int because it is an integer, it doesn't matter the size, then the number of bits, and underscore T because it is a type def. And if you wanted a signed integer, it's without the U, or a signed whatever. This goes for all data types. For example, if you want 16 bits, you have let's say short in 16. T. Right, so this is guaranteed to be at least 16 bits. For our intents and purposes, for this class, it's guaranteed to be 16 bits. Okay? This thing is guaranteed to be 32 bits. This thing is guaranteed to be 8 bits. And the U, or the lack of it, in front means treating it as signed or unsigned. It's good to get into the habit of using these data types instead of these. Because it makes intent clear, especially in the case where characters are involved. So in the following projects, where we will give you pieces of bytes, they will be unsigned car or maybe even car, but you do not treat them as strings, they're not text. Also, text is just signed bytes, so cards, with specific values. So if you look up here, ASCII hex table, okay, sure. Right, so where is A? Lowercase a is the byte 61. Capital A is the byte 41. Right? This is how text works. So here, if I print the same value, 0xff, right, as a byte, it's 255. As a signed byte, it's -1. And it's the exact same. It's this thing. It's 11111. Right? We're just reading it differently. This is what a data type is. It's reading those 0 and 1s in a different way. Okay, so here we creating a message. We create it on the heap. We don't care about the heap right now. It's just on the heap. We are setting data to 230, offset to 0.8. Okay. And here we create a byte array with some bytes in it, and then read the byte array as a message t. As a message, same thing as here. So if I execute to here, and come on. Do you see? Even though this is just a byte array, if I read it as a message, I get the result of a message. Now I made sure that these bytes are the exact same thing that would happen if you did this thing, right? Like I made it that way. But this is just to demonstrate that it's just bytes. And here we have our original message M, and now instead of the M is a struct message pointer, instead of a struct message pointer, we're saying, okay, read it as a potato pointer, and we're gonna print potato size. So if I print this, where is my output? I get 230 again. That's because a message at the very beginning has an integer, and I already set that integer to 230. So even if I read this piece of data as a potato, again the first thing is an integer, so again it's 230. I'm not changing the underlying memory, there is no copy created here. We're just pointing to the same thing, just reading it differently. Is this clear? It would sort of work in the sense that a float and an integer have the same size, are 4 bytes long, and you would get some integer back. You wouldn't get the same value, so you wouldn't get 0.8 or 0. You would get some huge value. Right, so it would still read the memory there, but you would get nonsensical data back. And here I'm doing something weird. I forgot to ask, is anyone not familiar with pointers? Let me quickly go over some stuff just in case, or maybe someone else that's watching this stream later. And so, well, worked and understand might be different for some people. So if I have a piece, if I have a piece of data here, let's say that this is at address 50, and it contains the bytes, I don't know, 80. And so we have a piece of data here. It contains the value 80, and it's located at address 50. Let's say that this thing is A. If I get a pointer to A, so ampersand A, the pointer is the address of A. What's the value of PTR? I have a similar example in code here, so we don't. Here, I have A. Let's say that A was this thing here at address 50. And then we have D, which is the address, is a pointer to an integer, and it's the address of A. What's the value of D? Go from this example here. So the value of D is 50 because that's where it is stored. Okay? That's all a pointer is. It's an address, a memory address. It doesn't matter what A is, it's just wherever A starts, basically. So a pointer is just, you can change A, D is still gonna be 50 for our example here on the Krita side. Oh no, 0x5 is not 50, it's just I gave it a random value. 0x5 would be 80 here. So the value of D is wherever A exists, so 50. It doesn't matter what A contains. Whether A contains 80 or 75 or a billion. Well, you specifically don't, the compiler does. This is what this syntax does. The ampersand takes the address of something. And if you have D is now a pointer, and if you do asterisk D, now you are going to that address, you are going to 50, and you are accessing an integer. Because D is a pointer to an integer. The address in this example is 32 bits because I'm compiling for 32 bits, as you can see here. If I was compiling for 64, it would be 64 bits. So the size of a pointer always depends on the architecture. So D will always be 4 or 8 bytes, and it doesn't matter what it points to. Since it is an address, it's either 4 or 8. 4 for 32 bits, 8 for 64. It doesn't matter how much memory it is pointing to. It is 4 or 8. End of story. And this is why whenever you create something on the heap, you get a pointer back. Because the memory is not there for you, it's on the heap. So you need the address of wherever that thing is. Right? Does that make sense? Yeah. I'm going to assume it makes sense since I'm not seeing any questions or anything. So here I'm getting the address of byte array, and I'm saying to my compiler, hey, you know what? This is a pointer to a message t. Because a pointer to the byte array and a pointer to a message, they are the same size. They are the same thing. Right? They're just an address. And then I'm asking my compiler here to read it differently. What the arrow does is first it dereferences the pointer, then accesses the thing. Same thing here. M is a pointer to something. I'm saying, okay, read it as a pointer to something else. A pointer is a pointer is a pointer. And here, even more weird pointer manipulation. There is no real reason to want to do that. Right? But you never know what you might encounter. And so we're getting P. We're saying, okay, P, which was our potato, which was our message, actually. P is now a character pointer. So increase this character pointer by the size of an integer and read that as a float pointer. Now, when you increase a pointer, you increase it by the size that it points to. So if you increase a character pointer, it will increase by one character. If you increase an integer pointer, it will increase by one integer. And what this will do is go to M, where M begins, skip one integer, the size of an integer, and read an offset, a float. Right, so this will just print 08. But this is weird. I have an explanation here, which we don't really care about. This works because, using the way Visual Studio compiles and all of that stuff, there are ways to get the compiler to give you that information, which might be useful for projects. I'm not sure if it will be, but you never know. So there are offset off macros in most modern compilers, which will tell you, okay, in struct message, how many bytes after the start of a struct message is offset. So where offset is 4 bytes after the struct of a message, of the beginning of a struct message. Damn it. So this is the correct way to do this thing. Okay, let's go to the next thing that you're gonna do wrong. Let me say this. Size of, as you can see here, is blue for me. That means it is a keyword. Size of is not a function. It is not a function. This is not something that you call at runtime. And it is definitely not the same as len in Python. Never use it as the same. Size of will just tell you the size of a data type. Okay. So I'm allocating here 5 bytes. I'm allocating here 400 integers. Everyone clear with this? And then I'm creating a stack allocated array of size 8. And I'm gonna print the size of all of these three. And so size of P1 is an integer pointer. So the size of an integer pointer is 4. Of a byte pointer is 4. The size of an integer pointer is again 4. It's a pointer. Every pointer is 4 or 8. And it doesn't matter how much memory you have allocated for that pointer. Now, here, the compiler figures out what I want to do because they are in the same scope, basically. Size of P3 and P3 are in the same scope. Size is in terms of bytes, not bits. It's 4 bytes. Yeah. So, the compiler here figured out what I want to do. The compiler was like, okay, this guy, he has no clue what he was doing. Let me fix that for him and replaced this thing with 8. Because it figured out that I wanted the size of the array and it had the information for the size of the array to give me. This thing here happens during compilation. It doesn't happen when you run. Right? So it happens when you compile your program. This thing will just be replaced with a number. And I can show you exactly that. So if I decompile, see, go to disassembly, see, it's just pushing 4. And then calls printf. There is no call to another function here. The compiler, while it was going through my code, it just removed all of that and put 4 in its place. The number 4, that's it. Is this clear? Size of will never give you the length of the array, with this one exception. When the array is allocated in the exact same place as the call of size of. If I make a function here, yeah, GCC will figure that out. It's not a C, a Microsoft only thing. Hello? See, now I passed this array to a function. And when it printed out the size, it no longer had the information of 8. So it put in 4 instead. That's why, because it's a pointer. An array is a pointer. Again, there is no thing such as an array. It's a pointer. Basically, this is just syntax to say, okay, put this on the stack instead of allocating it on the heap. Okay. And this is why we had the recommendation yesterday, I believe, on Discord. You should avoid using sizeof with variables. This is here to demonstrate the issue, but you should avoid using sizeof with variables. You should be using sizeof with data types because it forces you to think of data types. Because sizeof will only give you the size of a data type, not a variable. So this memory here that allocated, completely irrelevant. Next thing, move semantics. Now, from here on out, we're gonna see what we talked about on the prologue about the stack and stuff, about where the arguments are placed and all of that. We're gonna start seeing it a lot. So, I'm allocating size for 5 of my structs. Right, as you can see here, how many I want, and how big that thing is. So malloc takes the size in bytes. No, I won't make these files available. I don't usually do, because you can only run them on Windows, and yeah, it requires knowing how to use how to use Visual Studio and all of that stuff. But you can always rewatch the thing. Also, if anyone wanted to make some timestamps on the comments below, that would be appreciated. But I digress. So I allocate space for 5 potatoes, grab the one at 3, and change its size. Or at least that's what I think I'm doing. So, whoa. As you can see, I printed the size of P. And next thing, I'm going to try to print the size of potatoes 3. Right? As you can see, those are different. Potatoes and potatoes 3 was created somewhere on the heap because of malloc. P is a local variable. It was created here. When you do the assignment, locals is here and P is not a pointer. So what are you going to do? You're going to go to wherever this thing points and copy whatever data you find. Right? It's a CPU. That's what it knows to do. Move data around. So you copy whatever was in potatoes 3 into P, and then when I change P, potatoes 3 is still over there in the heap. It hasn't been changed. So I either need to copy P back to potatoes 3, or I just get a pointer to potatoes 3 and use the pointer to modify stuff. And now you're thinking with pointers. Right, so if I run this now, whoa, see, the change went through. Potatoes 3 is wherever it is, we don't care. We get the address of it. P underscore PTR is still a local variable, but now it's the type of local variable that points to another piece of memory. And I can modify both. Is this clear? No. Here. Let me move those out. Right? Is the difference between those two clear? Give me a second. Yeah, I'm just. We have a lot of stuff to cover, and I don't want to go too fast, and lose people. Although you can always rewatch it, it's better if you can ask your questions live. And let's go to everyone's favorite subject, malloc and free. We're gonna go to debug mode for this. What we have here. Come on. So we have a struct called player. No. This is just a dumb struct, just some stuff other than potatoes and messages. It's more, let's say, realistic. Not really, but anyway. So this is the layout. We have the position X and Y. We have some health, its attack value, and whether it is alive. And we're making a game. So we want to create some players, right? Okay, I'm actually recording this to my disk as well, just to be safe. But YouTube is supposed to be saving it. So, let's enable this piece of code. Where is it? And I'm gonna bring it here so you can see the actual piece of code. Ignore the rest for now. So we're calling create players. And what we're doing is we're creating an array of 5 players, setting up their X and Y values, and returning this array. And then this is just a loop that will try to print the players, so we can see it. Okay. So print player should not be called. This is the output. Is this what you would expect? Let me bring this here so you can see the code of create player. This should be, I assume, 0011223344, right? According to this code. Can you see what happened here? Let's say players. It has nothing to do with the reference. So players, actually, if you dereferenced here, like in the printing function, you would just get a segfault. Players is a stack allocated variable. It belongs to the frame of create players 1. When you return it, and you return from the function, you remove that stack frame to return back to whatever stack frame called you. Just lost this memory. Just lost players 5. That memory doesn't exist anymore. right? So you cannot return it. This is why I had, where is it? This warning disabled here. Actually, the compiler in here would yell at me and be like, hey, you're returning a stack allocated variable. You can only do that with primitive data types or struct. If I was returning one player, yeah, the compiler can figure that out and copy bytes over. Since now we're having an array, so we're having a piece of memory larger than one thing, nope, cannot return. You cannot do this. This is not a data type, right? As you can see, it already complains because I have no clue how big this thing is going to be. The compiler cannot return it. This is okay. That's one solution. So Neil suggested that we pass in a pointer. It's definitely one solution to it. But many will do this, especially starting from project 1. They will do this. And now you know why it doesn't work. You cannot return stack allocated memory. You can only do that with integers, floats, stuff like that, not arrays. And the reason you can do that is because the compiler knows how to copy them over, and your CPU by extension. Because again, you are copying stuff. This memory belongs to create players. This memory does not. So you cannot, do that. So let's go to our second attempt. Return a pointer. Bring that here. So this is create players 2. We get an argument about how many we want. We allocate that much memory. So we want 5 players, and each player is size of player, so we want 5 times size of player bytes. Set their values. Let's see what's gonna happen. Didn't pass. And we get the values we expected. Right, so that's mostly solved. Right? And if we continue execution, we are gonna get a nice error from our visual leak detector. So this is basically Valgrind. Visual leak detector is Valgrind for Windows. And it's telling me that I lost 140 bytes. This is 5 players, basically. Or 7, my bad. 7 players. And this is because we allocated the memory here. We used it in here, but we never freed it. So if I define cleanup, is that way? Nope. I need an underscore. If I free the memory, there is no more leaks. Now, it's important to note that I'm not freeing the memory here in create players, which is something that I've seen many people do, and they said that they have been taught that way. So you malloc something in a function, and you free it at the end. But yeah, that's pointless. If you want to use that memory elsewhere, you cannot free it, at least not in that function. You free the memory when you're done with it. And so I'm using it in main. Once I'm done and no longer need it, that's when I'm going to free. And this works mostly. Actually, this works exactly as we want it for now. The thing is that, especially in the kernel and in C in general, there is what's it called? A good practice, let's say. You use the return value to showcase error or success. So zero means success, something negative means an error, or something along those lines, usually. And that would mean that you need to pass in a pointer to this function now to do the allocation for you. And I'm showing you this way, this attempt, because you will have to adhere to this. Either use it, since you're using other functions like getLine, for example, or you will have to implement it probably in some of your kernel code. So main here creates a pointer to null and passes the pointer here, and you see we get the status back to see if it succeeded or not. And create players 3 is this thing. It allocates player space for 8 players in this case. Check for this, set the values, return 1 because everything went okay. Oh no, this is not the error that I was expecting, because to the startup. So we're stopped here before the printing. And let's continue. Whoop. An exception was thrown, read access violation. P was null pointer. P is the array of players, basically, in print. So it looks like attempt 3 here is still null, even if we allocate it in here. I want you to think back to what we talked about in the stack section, in the intro prologue, and try to figure out why this happens. While I take a voice break. Yeah. So we create a pointer here to null. We pass it into players 3. Players 3 allocates memory to that pointer, sets the value, creates players, all of that stuff, returns 1 because everything went successful. But here, when we try to access the pointer in players, the pointer is null, and we get a segfault. Yeah, it's related to the stack frame stuff. What are the ways you can pass arguments to function? Stack memory, a pointer to another block of memory, which we said is more or less never used in modern operating systems, at least for our purposes, and registers. So basically we have stack memory and registers. I can tell you that array PTR is going to be passed through a register because it's big enough to fit into a register. Well, small enough to fit into a register. Where is Krita? Here. So you can see the thing again. Right, so for stack frame, you have arguments. This includes registers for simplicity purposes here, and locals. Attempt 3, the value of attempt 3 is going to be copied into a register in this case, or it could be copied onto the stack space above the beginning of the stack frame. And as we said, when you reference local variables or arguments, you are referencing the beginning of the stack frame plus or minus some bytes. Right, so temp3 was here in main. Before I call link players 3, I copy it down here in a register or the stack frame, the stack memory. And then create players 3 references this copy here. So when I malloc, when I say array pointer equals malloc, I'm changing this copy down here. The original one in the main frame, the main stack frame, remains unchanged. It remains pointing to null. So once this function, create players 3, is done, cleaned up, attempt 3 still points to null up here. Hasn't changed a bit. So when I call it again on print players 3, I get the error. Is this clear why it happens? Sure. So we have our main function. We create the variable attempt 3 in that stack frame and set it pointing to null. Yeah. When I call create players 3, before I call create players 3, what we saw at the beginning is we create some space for the arguments. Right? In this case, attempt 3 is going to be passed through a register, but let's pretend that doesn't happen because it doesn't really make a difference. We create some space for the arguments. That space is new space, below whatever we called earlier. So we have attempt 3, the variable attempt 3 up here. We create some new space down here for the arguments. Copy the value of attempt 3 down here to the new space, and then call create players 3. And then create players 3 will just access this space of the arguments down here. It has absolutely no notion of whatever was up here, because it cannot know. You can create the create players 3 function from everywhere. So when it changes each copy of the argument here, the original remains unchanged. And so the value of create players 3 is copied in here in arguments, and the function references this value here. The original one, which is somewhere up here, never changed. This is literally the trickiest part of this session, and I really want you guys to get it. All the arguments ever all the arguments in any function are always a copy. That's it. They are always a copy. So array PTR, the value of array PTR is a copy of the value of attempt 3. They are not the same variable. They might have the same value at the beginning of the function, but they're not the same variable. They are not the same memory. Okay. And finally, let's see how you fix that, because obviously this would be a huge, drawback if you could not do what we want to do here. So we're gonna fix that with attempt number 4. And this is, let's say, the correct way of doing things, like this kind of allocation. So again, we create the variable attempt 4 here and have it pointing to null. But as you can see here, we are passing the address of attempt 4. And in create players 4, instead of taking a single pointer, we're getting a double pointer. Right? So now instead of changing the value of array PTR, we're changing where array PTR points to. And array PTR, since we're dereferencing it, and array PTR points to the value attempt 4. So now we're changing attempt 4. The whole copy thing still happens. The argument now, though, is the address of attempt 4. We're going wherever that was pointing and changing that, instead of changing our argument. Because our argument is just a copy. And we do the same things again here. And now if I run this, I'm not going to get an exception. It's going to work. Get all the 8. Everyone clear? Because a single pointer, so player T star points to a player T. A player T star star points to a player star. So let me get my let me create a new one. Okay. So originally we had our function here with its argument up here, and this argument was a copy of this value, of the red value over here. Okay. And when in here we were modifying our argument, we were changing this piece of memory and the original was remaining unchanged. Now on the second try, we have our argument here, our function here. We have some argument here, but this argument, which is a double pointer, points to this value here, which we said is gonna point to some memory, but ignore this part for now. Right. So we get our argument here, the double pointer, we follow it once, and then we malloc. here. Malloc will give you a pointer to a player pointer, so you follow the double pointer once and you change this. And this thing, the red thing, now belongs to main, and main has access to it. And so you follow it once here. And it's similar to the potato thing. Where is it? I don't remember. Here. When we wanted to modify this thing, we had to get a pointer to it. Right? So, as a rule of thumb, if you want to modify something, you want a pointer to that something. Now, if that something happens to be a pointer, then you want a pointer of a pointer. Okay, since it's getting late, it's like almost 9 o'clock. I'm gonna move on. If you have any other questions, type them here. Go over this again. You're gonna have the video. You can always message me on Discord. You can email me. It's fine. Okay? But this, if you get this depends on the stack thing we talked earlier. This is the trickiest part about C. This is where people get confused. The moment this clicks, you're done. C is the easiest language ever. And I'm not even kidding. It's so simple. It's the simplest language other than assembly. And assembly is also very simple, but it's complicated because, well, it's not meant for human computers. Now, if you've seen the get line, whoa, that's not how you spell line. If you've seen the get line function, right? The first argument is a pointer to a character pointer, basically. So you do this. And then some other stuff here. Right, so this is how you call get line. And the reason you do that is this. This is why, because get line is gonna change and allocate the memory for you and do all that nice stuff. Right? This is why. Or if you have some other functions like we will see soon where you have a struct that you want populated by some function, you give it the address of that struct. You don't give it the struct itself. And as a matter of fact, here is the example I was talking about. So we create a player P, set its X position to 10 and then Y position 10, and then try to move the player, which is just gonna add these values. It's 150, and if after I run it, it remains 150. It doesn't change while it should. And the reason it doesn't change is P and player are copies of each other. And not the same thing, just copies. Let me see. if I'm forgetting anything here. No, I don't think I am. Yes, you should, if you want it to work, as we'll see now, you should pass a pointer to the thing that you want to change and use that. You don't necessarily have to dereference it. You can use the arrow thing, which is a dereference, but yeah. If you are familiar with C++, you've seen this syntax in find, let's say, let's whoa. You've seen this syntax, the reference, the passes reference syntax. What it is doing is this thing. The compiler will replace this with a pointer, and wherever you pass the player, wherever you pass P, instead of passing P, it will pass the address of P. It's just syntactic sugar. And yeah, also it's used to communicate intent here that, hey, I want a reference to this thing, I don't want a copy. This is translated to this, basically. And now for my final trick of the night, I'm going to introduce you to object-oriented C. Now, this is a pattern that the kernel uses extensively. Yeah, the reference syntax does not exist in C itself. As I said, the kernel uses this pattern extensively, that's why I'm showing it here. And it's object-oriented in a lot of quotes. It's not really object-oriented because, you do not have private, you do not have inheritance, you do not have protected things. So, and where is my player? Let me... Wait, what? Oh, I'm not in the solution experiment. Yeah. So we can see the functions. So if you have a method, and you want to give it a player to modify, you have to pass the address of that. And if you name that argument as this, you have basic C++. This is what C++ does. Every class function that you create, when you compile, it injects the first argument as this, which is a pointer to the struct itself, and this is object orientation. Well, the basics of object orientation. When you have a private variable and you get an error that you cannot access it, it is because the compiler says that it is private and doesn't allow compilation. If somehow you force the compiler to allow the compilation, you could just access the private variable. It's just there in the struct. There's nothing protecting that variable at runtime. This is how C++ does its classes, basically. And you have the player construction function that gets the player and the arguments, and this should look very similar to C++ right now. Instead of player underscore constructor, you would have this, which is again compile magic and syntax. Same thing for move, same thing for attack. Yeah, I just renamed this, and that's why this is a keyword in C++, because it does this thing over here. Technically, it's not a keyword in C either. In C++, sorry. If you had a function that does not belong to a class, so go into a C++ program, and you have create a static function that does not belong to a class, and you can use this keyword to create variables, and they're just fine. You can create a variable named this in that function. No problem. It's not a keyword. And so you should generally try to do this if you can. So let's say we wanted to create a list of some sort. And now for the kernel, I can tell you that you do not have to create your own lists because there are lists already in there. You can use those. But I don't know. Give me another object type other than player. Give me something that could belong to the kernel. So let's say file. You could have a struct file, and you can add here whatever you as the designer. That's very important in this course. You are the designers of the solutions here, mostly. Like, we give you some guidelines, but as you've seen, we leave a lot of things to your discretion. And for good reason. You need to make decisions based on the theory that you see in class. Right? So you have some theory about drawbacks, about trade-offs. You need now to make a decision. How are you going to design this thing? So you have your file, you can add whatever you want in here. And that whatever is dependent on your system, your design. So whatever you want to make your system better. It could be IDs, it could be addresses, it could be anything. And then you just have functions that grab this struct and move it around and edit it and use it. You no longer need global variables for that. There are cases and there are things that you will need global variables for in the kernel. You cannot get around it. But if a file, for example, has a name and a size, and excuse my indentation right now, but like, and size and permissions, and I don't know what else, and you can put all of that in a struct and move the struct around in an object-oriented kind of way. And if you need lists of files, you just, location, true, whatever location might be in your system, right? And if you need a list of files, you just link the files together, because what we have currently seen is people making an array of names and an array of sizes, global arrays, and an array of permissions. And then they have indices to index these arrays. But now what happens if a file is new and has no size or has no name because reasons? Right? I want you to, if possible, start thinking this way. Start thinking I call it object-oriented way. It's not. C was doing this before object orientation was cool anyway. I just want you to start thinking this way, if possible. That will help your solutions a lot. This is not completely relevant to Project One, although you could definitely apply it if you wanted to. But it will definitely be relevant for the other projects. Oh, I mean, this object-oriented way. So you create a struct where you would create a class, for example. You create a struct and you create functions that operate in this struct instead of having global variables with attributes. Yeah. I mean, again, there are trade-offs. If you had a very limited amount of files, let's say, probably the index thing would be faster. But you could always create just an array of file structs and do that. So I see this a lot, people not abstracting stuff. Yes, I will quickly go into Valgrind. So I see this a lot, and I've seen students give up on something because they were not abstracting stuff and trying to think of the whole project or problem at once. And it doesn't help you abstract stuff this way. Create smaller functions that operate on smaller pieces of data. Now, and to show some Valgrind stuff before we end. I'm pretty sure Valgrind is already installed on your VMs because you need it to compile the kernel anyway. If it's not, you can just apt install Valgrind. Right? Let me zoom in here. So the way you use Valgrind basically is Valgrind and the executable you want. In this case, it's simply set. And it starts, and when you exit, when the execution finishes, it will give you a report. Now, the cell itself, actually, let me see if it's going to show here. Yes. No, it doesn't. So, as we've talked about in class, the idea of a cell is that you fork a child to execute the thing and wait for it in the parent. Valgrind will give you two outputs here. So if I had a memory leak in my child, I would get a different heap summary here. If my parent is 3551, I would get a summary from 3552, for example, or 3, somewhere along those lines. That means that this heap summary, this leak, comes from the child, not from the parent. This number here is the PID of the process ID. No, I mean next. Right, by default, it will tell you how many blocks were used, how many blocks were not freed if there are leaks. Now, as you can see here, I have no leaks. If you do have leaks, what you can use is, I believe is leak check equals full. and this will give you an overall report of different kinds of leaks. Like, I don't remember the names, so there is one called Definitely Lost. That means that you definitely lost and leaked that memory. There is another one called Used at Exit, I think. That means that while that memory was leaked, it means you were still using it at the exit of the program. So there might be a good reason for that, but usually in the kernel there is not a good reason for that. So you should at least be able to detect those and know where they happen and where. And the other command, you can use both of them, is whoop, no. Track wait, origins. Well, yeah, I mean that's what it means, Neil. What? Right? It's basically malloc without free. When you should have free, that's what definitely lost means. And the other, no, yes, the other command is track origins. That's going to be useful, and this will, if you have leaked something, it will be able to tell you where you mallocked something. It won't tell you where you should free it, obviously, but it will tell you where you leaked it. Now, this will not work for my example here because of reasons. If we go to the make file that we gave you, I said the make file that we gave you here. If you have this -g for debug flags on, when you compile, track origins will probably work for you. If you don't, it won't. And also, you will see it will start complaining about mallocing stuff that was already mallocked. There is a bunch of errors that you can see. We can talk about them, and you can ask questions about them on chats as they come. Yeah. Let me copy this here. Now, where is my solution explorer? New item. So, yeah, wait, what? Okay, ignore all the squigglies and the syntax errors and all of that stuff. So you have utils.c, right? So you just add a space and utils.c here. Do not add any header files here. And if you add header files, when you run make clean to clean up your stuff, it will delete the header files. There are ways to fix it. There is no point going into that. Just do not add any header files here. Yeah, just a space and the name with a C at the end. .c. And if it's in a path, so let's say you have a folder code.c, you can add that as well. And this path is relative to wherever the make file was. So just space and name. I think that's all I had to cover. It's been 2 hours now. Yeah, if you have any questions, you feel free to ask them now. Otherwise, you can always go over the recording when it's published, and you can come on Discord and talk to us there, or ask on Piazza. Although there is not a lot of context on Piazza, you can email me. But yeah, for Project One, you definitely have a make clean target. It will clean out all the compilation artifacts and the binary. If you are not on Discord, join the Discord server. That's where you can find all of the TAs. And if you want real help during office hours, that's where you're going to get it. Unfortunately, you need to share your screen with us, and we need to share our screen with you. And that's very easy on Discord, not so much on Piazza. Okay, yeah, if there are no more questions, thank you guys for coming. I would appreciate, as I said, if someone made some timestamps when the final thing is released. I'll try to edit some of the, empty silences and stuff if there are any, but I'm not really good at that. Okay, so I'm gonna stop the recording. Have a good night, and yeah, I'll see you in class.